The YouTube recording is on. There we go. And today's main topic is going to be this particular module here. If you go to Canvas, the module that we are on at this point is big O, omega, and theta notation. And this is the first one that we are going to focus on today. So this is the notes. I just changed a few things, to improve the readability of my notes. So if you had downloaded one or printed out one already, you might want to check out the changes and see if it is worth the time to download it again and print it out again. But I just want to let you know that I just updated it a few minutes ago. All right, I hope everybody is doing well. We got about 30 seconds to go. And this particular topic is actually quite important, not only because it is a part of CISP 440, but also because you probably want to understand time complexity throughout your entire software engineering or software developer career. This is a big deal. Okay, this is what makes or break a program. All right, so it is noontime. I'm going to get the lecture started. This is a brand spanking new topic, and we are not going to spend, well, I shouldn't say that, but we are not going to spend as much time as I would like to, on this particular topic, because there are some additional topics that I also want to spend some time on. But I cannot ignore this one. With predicate calculus, I can kind of go like, well, maybe we don't need to understand it because the application of predicate calculus is somewhat limited. Okay, but with time complexity and the concept of the big O, big little omega, and big theta notation, that I cannot say. Okay, I have to say that this is a lot more important compared to predicate calculus. Even graph theory is not as important. Any questions? Nope. Okay. All right. So what we'll do is we are going to get started with this module. And section 2 really is just a step-by-step introduction to the concept of what we mean by time complexity. Okay, so when you look at this algorithm, okay, which is expressed in C syntax, it's really just a loop to go through an array, and then we just add up all the values of all the elements in the array. Okay, William, your mic is still on, so I think we can all hear the background noise.
Sorry about that.
No problem. Thank you. All right. So with this loop here, we want to analyze and go like, well, what if I increase n? Okay, if I change this n here, which is either a pound defined, a macro, or a constant that I define somewhere else in the program. If I double this n, how much time is it going to take? And if I quadruple it, how much time is it going to take? So when we analyze this algorithm, there are certain things that would take constant time. Okay, so what would take constant time would be things that are outside of the loop. So the initialization of I is going to take constant time. The initialization of sum is going to take constant time, and the amount of time to allocate for the variables, whether they're local or global, would also just take constant time. So those are the constant time items, which in the rest of this text here, I refer those as T1 and T2. So T1 is specifically referring to the initialization time of line 4 and line 5. So that's basically here. Okay, so I'm just jumping around a little bit because I know all of this is already documented in the text, but when I'm describing the algorithm, I'm looking at the algorithm itself. And then line 6 is the one that is kind of an oddball because you might think that it would just run n times. Well, the answer is no. It actually runs n plus 1 times because the loop needs to go back to reevaluate the condition one time more than the number of iterations, because the last one is going to have I is less than n failing, getting a false value, and then that's the reason why we get out. So it's going to be true for n times, and then it's going to be false for the last time, and that's why I is less than n is actually evaluated n plus 1 times and not n times. So that part is reflected here. Okay, every time we compare, we assume that it's going to take t subscript 2 amount of time, and that's why we have t2 on the outside, and then we have t2 basically multiplied by n as well, just to take care of the n plus 1. And then we have T3. Okay, so T3 is referring to the amount of time when we combine line 8 and line 9. The amount of time for each iteration is going to be combined into what in the text here is referring to as T3. So if we can figure out, okay, if you look at the actual opcode generated and take into consideration optimization in a processor and all kinds of stuff like that, we can come up with T1, T2, and T3. And then this number here, okay, when you look at this expression, that will give you the exact amount of time that it takes to execute this algorithm, and using n as a parameter. Okay, so this is great, okay, because we actually get the exact amount of time. But sometimes algorithms get complicated. So when you look at the bubble sort algorithm, we are moving on to section 2.1 at this point. So when you look at the bubble sort algorithm, okay, it's broken up into T1, T2, T3. T1 is a constant time, which means it is not related to n at all. T2 is proportional to n, and then T3 is proportional to n squared. So if you can figure out T1, T2, and T3, then obviously you can figure out the exact amount of time that it takes to perform bubble sort. But it's tedious to do something like this. In other words, most of the time, we look at something that does not grow with n and go like, well, that is somewhat negligible. Okay, when n gets really large, the proportion that T1 contributes when n gets large is going to be smaller and smaller and smaller. Even T2 is not going to contribute much when n is becoming a really large number, because T2 is only multiplied to n, whereas T3 is multiplied to n squared. So, this is kind of the idea of time complexity. Is a lot of times we don't need to know the exact amount of time that an algorithm is going to take with a particular implementation. A lot of times we just need to know approximately how bad or how good is this algorithm, and typically we are comparing algorithms to each other. Okay, so we want to say, okay, given algorithm 1, 2, and 3, which one should I use? Which one is the most efficient? Which one is the fastest? Okay, so when we compare algorithms, when we're moving on to section 2.2 at this point, we typically don't want to know what is T1, T2, and T3. We don't even want to know that there's one component that is proportional to n, because if f of n, if we have a time complexity that is like this, which is bubble sort, and then we have another time complexity that is like this, which describes a whole big variety of sorting algorithms, including merge sort, heap sort, and stuff like that, then we go like, well, do we really need to know what is T1, T2, and T3 in each case? And the answer is no, we don't need to do that. So the rest of today's lecture, with this module, is really establishing the mathematical background of why do we not need to know, the details, okay, T1, T2, and T3, and how do we describe an algorithm? How do we describe the time complexity of an algorithm when we don't need to know exactly how much time it takes? We just need to know, well, it is kind of like this, okay? So what kind of are we talking about? Okay. So the rest of this discussion is really just talking about, when n is large, n squared would eventually be greater than, n log n. Okay, even with a big huge constant in front of it, eventually you can find an n so that an algorithm with an n squared time complexity is going to be beaten by an algorithm that runs, with n log n time complexity. So I can give you an example, okay, but I want to kind of keep talking about the abstract concepts first, and then I'll give you an example if we have time at the end of today's lecture. Okay. So now we move on to terms and all kinds of crazy notation in math. Okay. So the first thing we talk about in section 2.3 has to do with asymptotic estimates. Okay, in many cases, we only care about the time complexity of an algorithm with respect to the input, and we just want to know, well, if you make the problem bigger, how much time is it going to take relative to when the problem is smaller? And then we also compare two different algorithms or multiple algorithms given the same size. Okay, um, and that's basically saying, okay, we're looking at the behavior of an algorithm as the size of the problem get bigger and bigger and bigger. Okay, so that is basically an estimate of the behavior of the algorithm. We are no longer looking at the exact time. We are now looking at a trend of the time complexity. All right, so I'm just going to pause here to see if there are any questions. I don't see anything in the text channel, but if anyone has any questions, this is a good time to ask. Particularly, I think it's important to understand the importance of understanding time complexity. So are we still doing okay with in terms of understanding the importance of the time complexity, not so much how it is calculated. Okay.
Works for me.
Okay, great, thank you. All right, so section 3 is a little bit crazy, in terms of, introducing terms and notations and whatnot. So we're going to have to go a little bit slower, with section 3. And also at the same time, it is kind of important to relate section 3, all of these terms with what we are talking about, why it is important. Okay, so we'll start with some notations that is used throughout section 3. So f of n in section 3 is always referring to the actual time complexity of an algorithm. In other words, when you look at f of n, it is giving you the exact number of milliseconds or microseconds that a particular algorithm needs to needs in order to finish, given the size of the problem is n. So f is exact. Okay, so g of n, okay, over here, is usually a much simpler approximation of the time complexity of an algorithm. So now what we want to do is to say, okay, I in theory know what f is, okay? And I can now say, okay, I given a certain g of n, how does f relate to g? Or in some cases, we may not even know, exactly what f is. We have a general idea of what it is, but we want to somehow relate it to a simple g of n and see how they relate. Okay, so just remember, f of n is the exact amount of time, which sometimes is very tedious and difficult to find, and g is a very simple function, like n squared, log of n log n, that sort of stuff. And we want to find out, how f of n relate to g of n. That is the whole purpose of the notations of big O, big omega, and big theta. But before we can get to the big O, big omega, and big theta concepts, the first thing we need to do is to introduce two terms. One is called supremum, and then the other one is called infimum. They're basically mirror images of each other. When we understand one, the other one is pretty much kind of the same thing, except it's on the other side. It's kind of like a mirror image. So what we'll do is we are defining A as a partial order. Now this is also partially why it is important to understand relations, because now we are reusing terms that we have introduced when we talked about relations. So A is a partial order, which basically means it has certain properties. It has to be reflexive, it has to be antisymmetric, and it also has to be transitive. Okay, but it only has to be a partial order, it doesn't have to be a total order. Okay, and then what we do is we define a subset of A. It can be exactly the same as A, but it has to be a subset. So A has some of the elements of A, and there are no elements in X that is not found in A. Okay, so we need to establish that X is a subset. So now we define a predicate. Okay, so once again, this has nothing to do with predicate calculus. Uh, a predicate is no more than a function that returns a boolean. Okay, so from the programming perspective, this is how you can relate what a predicate is to concepts that you have already understood a long, long time ago. Okay, a predicate is nothing more than a function that returns either true or false. Okay, so in this case, we have p of yx defined to be for every x in x, x is less than or equal to y. So it is just returning a boolean. And I know that I changed the notation. I use a colon here instead of using parentheses. So let me fix that first. Okay, I'm just fixing it on the side because you guys don't really need to know uh, how I make that change over here. So I'm just going to make a quick change just so that we are consistent in the use of notation, and I might have to do it several times because I think I used the colon notation several times in my notes. So oh, that won't work. There we go. Nope. One more time. Publish. There we go. All right, so I'm just gonna refresh. Get to the same place. There we go. So this is where we were talking about. So I just changed the notation a little bit. Instead of using colon to mean such that, I just put the such that in parentheses after the quantifier, which is the way we have been using quantifiers since the introduction of quantifiers in this class. So so are there any questions about the predicate p? Okay, what that really means? No questions? Okay. So P returns true if and only if y is the upper bound of the entire set X. That's all it is saying. Okay, so this particular P is saying, if Pyx is true, it means y is an upper bound of all the elements in X. Now, the next question is, well, can't we just use the word maximum? Well, it's not exactly a maximum because y does not have to be in X. Okay, so y can be in A but not in X. In order to fit this description. Okay, so now we introduce another definition. So this is the other definition. The other definition is the definition is this part here. Okay, the term or the notation we want to introduce is this part of the notation. We basically is saying lowercase s is the supremum of X. Okay, well, what does that mean? Okay, this is just a notation saying that s, which is a single value, is the supremum of X, which is a set. Well, this is the rest of the definition. Okay, we can call s as a supremum of X if and only if this portion is true. Okay, so now we need to kind of read this portion here and find out, okay, what exactly is it saying? So the first part of this is saying PSX. Well, it doesn't say it's true, but that implies the PSX has to be true. So if PSX is true, that means S, which is called the supremum of set X, is indeed the upper bound. Okay, so we know that S is the upper bound. What about the other part of this? Okay, so the other part, which is this part here, is saying for every S prime such that P of S prime X is also true. If that is true, we better make sure that S is less than or equal to S prime, which is a very, I guess, if you're not used to quantifiers and mathematical notations like this is a very obscure way of saying that S, not S prime, okay? This is saying that S is the smallest value that meets the requirement of being an upper bound of x. So let's pause a little bit here, and in case anyone has any questions, this is also a good time to ask. So let me just rephrase or repeat what I just said. S is called a supremum of a set X if and only if it is the smallest possible upper bound of set X. Are there any questions about what S is?
Not S itself, but
Mm-hmm.
how do we determine S prime?
So S prime is not quote unquote determined. So S prime it's bound by this for all or universal quantifiers. So basically, we look at everything under the sun in the entire universe, and we say, okay, let's consider that thing as S prime. Okay, so that includes a lot of stuff that really does not matter to us. But then, because we have an implication here, that means if S prime is an upper bound of X, okay, then we have some additional conditions to evaluate. Does that make sense? Because an implication is true um, if and only if the left hand side is false. Now, if S prime is not a upper bound of X, we are not interested in S prime at all. So we're only interested in all the S primes that are actual upper bounds of X. Now, if S prime is an upper bound of X, then we also want this additional quality to be true in order for the entire definition to be true. So the additional part is saying whatever S that we talk about over here has to be less than or equal to S prime, which is the thing that we are evaluating right now. So this entire part, okay, is really just a fancy mathematical way to say that S is as small as it can be, but still being the upper bound of X. Is that making any sense?
Yeah, I think.
Okay, all right. So you can look up the term supremum, using just Google. I'm pretty sure Wikipedia has a page on supremum or the concepts related to supremum. So it's you can check out alternative definitions. Um, S prime is also an upper bound of X. Yes. So Krishna is correct that this qualification basically means S prime is also an upper bound. But just being upper bound can be way upper bound. Okay, so I can give you an example. We can have we can have an infinite number of upper bounds. Okay, so that's a very good question, Krishna. So let me give you guys an example. Okay, I'm just gonna let me see which notepad I can reuse here. Yeah, we can reuse this one. Okay. All right. So let's go ahead and take a look at a particular example. So let's say set A is really just 1, 2, 3, as numbers. Okay. Um, and we can define the relation, to be just less than or equal to. Okay, so we're looking at less than or equal to as the relation. So you can definitely tell that A is, okay, I should say less than or equal to as a relation over A is partial order. In fact, it is total order, which we don't need, but it is definitely partial order. So that is it's established. Okay, this is um, a partial order relation over set A. Okay, so that's pretty easy to see because A only has integers, and we can easily compare two integers and less than or equal to. When we apply that to integers, it's a partial order. It's a total order, which means it implies it is a partial order. So we'll even say that x equals to A. Okay, so we can just say that. Okay, or better yet, we can say x is a subset. So we'll just look at x as just 1, 2 without the 3. Okay. So now we want to say what exactly will meet the requirement of being a supremum um, of x in this case. Okay, so we look at the notation supremum of x. But before we talk about supremum, it is also we need to go back and find out what is p of something. So we want to go back and look at p, the predicate. So this time we're going to substitute actual values into the parameters. So instead of just saying p y of x, we're going to say exactly which y we are talking about. Okay. So we'll look at something like 1, okay? And then we look at the set x. And what do you think is the value of the predicate p applied to 1 and x? Well, first of all, what is the type of the value this function is supposed to return? It's supposed to be a boolean, and Krishna got it. It is a false, okay? Because 1 is not an upper bound of all the elements in x, okay? Because, hey, you're just within x. 2 is already greater than or equal to 1. So, 1 does not meet the requirement of all of that. So let's look at p2 of x. Well, that is true, okay? Because when we look at the definition of p as a predicate, or if we prefer to look at it as a function, um, okay, so if s, okay, let me go back to this definition over here, and let me move this so that we can see both. There we go. So we can see both. So when y equals to 2 and x is the same as this x here, which only has elements 1 and 2, then we can claim and say for everything in x, which is just 1 and 2, that thing, lowercase x, is indeed less than or equal to y, which is 2 in this case. So 2 is, basically we're saying 2 is greater than or equal to everything in x, which is true in this case. But we can also say, what about p3 of x? Okay. So the value y does not have to be an element of x. Okay, it can be outside of the set x here. So this turns out to be true as well, because 3 is greater than 1, 3 is greater than or equal to 1, 3 is greater than or equal to 2. So 3 also meets the requirement, basically the requirement of this particular predicate. So in general, you can have a predicate where a lot of values can make the predicate true. So now, which one do you choose as the actual supremum? That is the question, okay? And as it turns out, the way we choose which unique value to be the supremum over a particular set is the smallest value that is still an upper bound of the set itself. So is that part understood? Okay. So we got one confirmation, but if anyone does not uh, get the general concept, this is a good place to ask, because this is laying the foundation of all the other stuff that we're going to talk about for this particular module. Okay. It's the smallest of all of the upper bounds, basically. The supremum is the smallest of all the upper bounds. So 2 is the actual supremum. Yes, Krishna is correct. So in this case, the supremum of x, which is just 1 and 2, is just 2, because 2 is the smallest of 2 versus 3, because we only got 2 elements out of A that meets the requirement of P, but of those 2, 2 is the smallest, so 2 becomes the supremum over x. So is it always the largest value in the set x? Um, hmm. I think that is the case if A is a total order, but if A is a partial order, that is not necessarily the case. In other words, the supremum over x, of x can be an element in A, but it is not an element in x. So does that answer the question, Bo?
Yeah, I think so. Thank you.
Okay, excellent. Okay. So for the most part, okay, so even though technically, supremum of x is not technically the same as the maximum of x, when we are dealing with integers and real numbers, it is. Because integers, if you look at less than or equal to as a relation defined over integers, natural numbers, real numbers, rational numbers, and so on, it is a total order. So if it is a total order, then the supremum is the same as the maximum. Okay, now I don't have the proof of that. Okay, but it seems to make sense to me that the maximum of a particular set uh, is automatically the supremum of that set as well. So it sort of makes sense. All right, so shall we move on? Okay, so now we move on to infimum. Okay, so we move on to infimum. So infimum is kind of the flip side. So when you look at the infimum of x, it is sort of the same thing as the minimum of x. Okay, so supremum is the maximum, and then infimum is the minimum of a particular set. So I'm not going to go through, what is Q and the quantifiers and stuff like that because it's just the flip side of that. Are we good so far with supremum and infimum?
Is A still partially ordered and all that as well for the infimum?
Yes. So we have to reuse the notations A and X. So A still has to be a partial order, and X is a subset of the partial order. But X can be A itself. Okay, it just has to be a subset. It doesn't have to be a proper subset. Are we okay so far? So for all
Yep, I was just making sure.
Yeah, that's good. So for all practical considerations, supremum is maximum and infimum is minimum. Okay, because we are only dealing with uh, uh, numerical values that are total orders. All right, so now we move on to section 3.3, which is something that I hope your pre-calc class has talked about, which is the limit of a sequence. Okay, so first of all, we'll introduce the concept of a sequence, an infinite sequence. So the concept of an infinite sequence, in this case, the sequence is x. Okay, so it starts with x lowercase 0 or bracket 0, x1, x2, x3 all the way, but the sequence doesn't, it will never run out. Okay, for any x of n, there's always a next value, which is x of n plus 1. So it keeps going and going and going. Okay, so do we understand the concept of an infinite sequence in this case? Are there any questions about what is a sequence and what makes it infinite? No questions? All right. So with an understanding of what a infinite sequence is, now we basically ask, if I just make I, which is the index, going through the sequence, approach infinity. In other words, I just make I going larger and larger and larger and larger. If I say, the limit of xi where I goes, approaches infinity equals to k, what does that mean exactly? Okay, because this is the notation. Okay, what you're seeing, what my cursor is bouncing around, is a notation. Okay, the notation has no inherent meaning. The meaning has to be defined using terms and notations that we already understand. So this is the question. Okay, what does this notation mean when I say, the limit of x of I when I approaches infinity is k? What does that mean exactly? Okay. As it turns out, one way to express that is to look at this mathematical notation over here. And yes, I personally really like to use mathematical notations, because it is concise and it is also very precise. Okay, which is good and bad. Okay, because being precise means there are no two ways to interpret the same thing. Which means if I make a mistake, I cannot fudge my way out of explaining that. Okay, if I make a mistake, I make a mistake because it is just wrong. Okay, but that really is the basis of mathematics. Okay, nothing should be fuzzy. Nothing should, no one should fudge anything in mathematical proofs. Okay, so this is the definition. So we'll go through the mathematical definition first, make sure that we understand each component, and then we'll say, okay, can you decode this? Can you translate this into natural language? Okay, then we'll move on to talk about the second part, which is in English what that means. Okay, so we'll go through the mathematical definition first. So the first part is a quantifier. Okay, we already understand what a quantifier is. So this one is basically saying for every epsilon that is greater than 0, okay, and epsilon is an element of the real number set. So all it really is saying is for every real number number epsilon that is greater than 0, okay, it is not 0, okay, it's greater than 0, it has to be greater than 0. The following has to be true. So what do you mean by the following has to be true? What is the following? This is the quote unquote the following. Okay, so the following has another quantifier. Okay, this is another quantifier. This is basically saying there exists a lowercase m that is a natural number. Okay, so for every epsilon that is greater than 0, there exists a natural number m such that what? And then we have another quantifier here. Okay, this is another quantifier, which is basically saying if you consider every single j that is at least as large as m as a natural number, the following has to be true. Okay, this following has to be true, which is k, which is the constant coming from this notation here. The difference between k and x of j, remember x is an infinite sequence, and j is just an index. Okay, j is just an index into the sequence. So the difference between k, which is the constant that we are interested in, and the value of that particular element in the sequence, it has to be within epsilon away from k. Okay, this is the absolute value symbol. Okay, so this bar has nothing to do with cardinality. This is really just your absolute number. Okay, so we're looking at something that is a triple that has a triple quantifier, nested quantifier, where it is for all there exists, and then for all again. Okay, and then we look at a simple equation or the simple comparison here. So what does it mean? Okay, so we'll start with the most casual way to look at this. Okay, so we'll start with this one here, which was one of the things that I just introduced within half an hour before the class started. Okay, so it's basically saying once we get to xm, all the other values of x in the x sequence are within epsilon of k. Give me any epsilon, I will find you an m such that if you look at xm, xm plus 1, xm plus 2, xm plus 3, the difference between all of those values in the sequence of x they're all within epsilon of k. Is that concept understood? Do we have any questions about that concept? Does anyone want an example, for this particular concept?
Yeah, could I get an example, please?
Yep. Okay, so we can look at certain examples. Okay, so let me. I'm just trying to find out, what is the easiest or the quickest way to get to a spreadsheet. So Calc is fine. It's faster than Google Spreadsheet. So we can look at this. So we want to look at I as a column. So I goes from 0 and keeps going and going. Okay, so we'll just say this is the previous cell plus 1. Okay, and then we look at column B. Column B is is x of I. Okay, so in this case, x of I is defined to be 1 divided by 1 plus whatever I is. Okay, well, this is so that I don't have a problem with I being 0, so everything is critical off by 1 in terms of being the reciprocal. So x of I is approximately the reciprocal of I, but not exactly, so that I don't have to deal with division by 0. Okay, so none of this is really surprising, right? So if I just make an example of this particular sequence, I can give you up to like 20. Okay, and this is not really surprising. Okay, do we have any questions about column A and column B? I is the index into the sequence, and the x of I is the value of a particular element in the sequence. No questions? Okay. Can everybody see that I can potentially go on and on and on and never ends? Okay, in theory, it can go on and never end, right? Okay, so x of
Yes.
I can keep going like that as well. Okay, but you can also see how x of I is always getting smaller and smaller. Okay, so one thing that I can claim in this case, okay, so I'm gonna put it in the spreadsheet as well. So I can claim this now. Okay, so I can claim if you take the limit. Okay, and I'm using the LaTeX syntax here, which is a little bit awkward. Well, this is partially, the LaTeX syntax. So the subscript or the underscore is basically saying whatever is in the curly braces or a subscript of limit. Okay, so we are saying that I approaching infinity. Okay, and then you look at x of I, and I claim this is 0. Okay, so k is 0 in this case. The sequence is as I approaches infinity, the limit of this sequence is 0. Okay, seems to make sense, right? I mean, if I make I larger and larger and larger, x of I is going to get closer and closer and closer to 0. Does that make sense? Just intuitively, does that make sense?
Yes.
Okay, excellent. So you can do a plot too. I mean, this is a simple spreadsheet to recreate, and you can do a plot, and you can see how the curve is going to get shallower and shallower and get closer to and closer to 0, but it will never reach 0. Okay, and this is the really cool part of the concept of limits is it doesn't really get there. Okay, because for any specific index I, 1 divided by I plus 1 is non-zero, but yet I can say that the sequence is approaching 0. Okay, so now how does this relate back to the description here? Okay, how does it relate back to uh, this complicated way to express something like that? Okay, so what I want you guys to do is to pick me an epsilon. Okay, so just give me an epsilon. Epsilon. Okay. So we can pick a very small epsilon value. Okay, well, I will just kind of randomly pick 0.002. Okay. Um, Now the other thing about epsilon is it has to be greater than 0. Okay, epsilon is can never be 0. It can be very small, but as small as it can be, it cannot be 0. It has to be greater than 0. So now the question is, okay, according to the definition, it's saying it'll give me an epsilon and I will always be able to find an index m such that x of m is within epsilon away from 0 in this case because k is 0 in this case, and then m plus 1, basically starting with m, all of the values, starting with x of m are going to be within epsilon away from 0 in this case. Okay, so I can solve this using algebra, but I'm not going to do it. Okay, because I want to show you the brute force way of looking at this, which is actually appropriate in this case. Okay, so the brute force way to look at this is to say, okay, let's make a condition over here. Okay, so the condition that I'm evaluating, this is the description of the condition, is if I look at the absolute value of x of I minus k, is that less than epsilon? Is it less than or less than or equal to? It's less than. Okay, that's fine. Epsilon. There we go. So column C is going to be something that is either true or false. Okay, it's really just asking, is the value of column B within less than epsilon away from k, which in this case is 0. Okay, so we'll go ahead and look at each one. Okay, and we ask the question. Okay, we look at B. So we ask if I subtract now. Technically speaking, you have to use the absolute value function, but since k is 0 in this case, you don't really have to use the absolute function. But I'm just going to put in the absolute function, just so that it is consistent with how it is defined in mathematics. So when you look at the absolute value, you're now asking, is it less than epsilon? And epsilon is this particular value here. And I'm going to put a dollar sign in front of the 3 so that when the formula is copied and pasted into different cells, the row number of E3 does not change. Okay, that's what the dollar sign is about. So now I can go, okay, so let's double click this. And you can see how it is false. And then, oh, I picked a value that is really small. Okay, so we have to keep going for a while. We're getting there. Uh-huh. Almost. Now, it's going to take more and more entries. The closer it gets to zero, the slower it is going to approach zero. But at some point, it does. Okay, so if I scroll back, now remember, we can always solve this, using algebra, but I intentionally did not solve it using algebra, but using the brute force approach, because it basically the point is at some point we'll find that m. So in this case, the m is right here. When we get to x 499, uh, that's the last one that did not meet the requirement. But starting with x of 500, um, the everything including x of 500, everything including that and onward in the sequence will meet that requirement. So is this kind of demonstrating the concept of limit? Yes or no? Okay. Not okay. We got a yes. Are there any no's? Are there any? Hold on. Give me a second to digest this. Okay. There are none of those. Oh, hold on. Okay. All right. So, but this is only for one particular epsilon. So the question is, what if I make this epsilon even smaller? Okay. I bet you cannot find such an index if I make it half the size. Okay. So we have 0.001. Okay. So if I change the epsilon, how do I choose epsilon? I don't. I only choose an epsilon in this case, as a visual demonstration, but epsilon can be any real value that is greater than zero. That's all epsilon needs to be, is greater than zero as a real value. So in this case, I just found my index. I found my m. M has to be 1000 in this case in order for x of m and everything after that to be less than epsilon away from zero. So you might say, okay, fine. So if I go back and change epsilon again, and this time we change epsilon to an even smaller value, okay, so we'll make it we'll add one more zero, okay, then all the numbers that we have explored would not make this condition true. But does that mean we cannot find the index? Nope. I can still find the index. I just have to extend the sequence a little bit longer. Then it will find that m, and then everything at xm and after will be less than epsilon away from my k, which is in this case 0. So is that answering the question? We do not choose epsilon. Epsilon is nothing more than um, a intermediate variable that we need in order to express what a limit is. It's basically just saying you can pick any epsilon that is non-zero, make it as small as you want, okay? As long as it is not zero, I can find that m, which is the index of x. Is that okay? Does that kind of explain the role of epsilon in the definition of limit? I'm guessing we're okay. Okay, kind of. Okay. So this is, I'm hoping this is one of the concepts that was at least introduced in pre-calc, because calculus itself is completely, okay, the basis of calculus is based on limits. I'm not sure about the epsilon delta proof because I have not been in touch with calculus for a long time. But I know the concept of limits, and this is the concept of limit is you basically just say that pick me any epsilon that is greater than zero. I'll be able to pick an m so that everything at m x of m and after would be within epsilon away from k. Okay. And then Peter has a question. Wouldn't the limit always be zero? No, it depends on the function. It depends on what the sequence is about. Okay, and there are some sequences where there's no limit. Okay, so we'll take a look at problems like that. Okay. Um, any other questions before we move on? Okay. If there are no questions, then we'll go ahead and take a look at an infinite sequence that has no limits. Okay, so the sequence x of I is defined to be negative 1 to the power of I. So you can see how this is just going to alternate, right? Because x0 is 1, x1 is going to be negative 1, x2 is going to be 0 again, x3 is going to be 1 again, negative 1 again, x4 is going to be 1, x5 is going to be negative 1. So it's just alternating between negative 1 and 1. So in this case, there's no limit value because it doesn't, the function does not converge to a particular value as it goes further and further and further away. Does that make sense? This one just it keeps oscillating without the oscillation, diminishing in any way. Is that okay? All right. So now the question is, well, what if we have a function that looks kind of like this? It keeps flipping and flopping. It never really quote unquote settles, on a particular value. Then it has no limits. Then how do we describe this kind of infinite sequence? So that is why we have section 3.4 and section 3.5, because those are the terminology that we introduce in order to describe the behavior of an infinite sequence. Even if it doesn't converge to a particular value, we can still define certain things and describe the properties of that infinite sequence. All right? So this is an example. Okay, let me highlight which part. This is an example to illustrate why only using the limit of a sequence is insufficient. Okay, so let me just pause here because earlier I said let's make sure that we can relate the concepts back to the problem that we have, which is how do we describe the time complexity of an algorithm. So now the question is, what does sequence have anything to do with time complexity of a particular algorithm? What are we talking about here? Okay, does anyone want to give it a guess? How does this connect to time complexity? What do you think is the index of an infinite sequence? How does that relate to the time complexity concept? Does anyone want to give it a try? Okay, Peter's typing. All right. Because as the input gets larger, it means the constant can be disregarded. So I think Peter is on to the concept, just did not describe it um, using the concepts, in an infinite sequence. Um, the size of the problem, which usually is an integer or a natural number, is the index of the infinite sequence. So x of 0, let me just go back to here. X of 0 is asking how much time does it take to run the algorithm when the problem size is 0. X of 1 is asking how much time does it take to solve the problem when the size of the problem is 1. So x of n is asking how much time does it take to solve the problem when the size of the problem is n. Okay, so f of n from the previous discussion is x of n in using the concept of a sequence, because the problem size, I guess there might be some problems where the problem size itself is not a natural number, but for the most part, the problem size is a natural number. How many elements do we have in an array? Okay, that's certainly a natural number. So is that okay? Does everybody see how the infinite sequence is really just the time complexity for each size of the problem, and the size of the problem can approach infinity, which means we'll make the problem larger and larger and larger. How do we describe how much time it takes to solve the problem as the problem size itself is getting larger and larger? So are we relating these two concepts? Are we relating the concept of the infinite sequence to the time complexity of an algorithm given a certain size of the problem? Yes, maybe. Okay, good. We got a confirmation. All right, so now we move on to some even more obscure ways of describing uh, the limits of a particular infinite sequence. So the first one is in section 3.4, it is called limit superior. So limit superior, which is abbreviated as limsup, is defined as this. Okay, so let's take a look at this definition here. The next slide actually helps to describe what it is, but we'll go ahead and take a look at this description here and find out, well, how do we decode this thing here? It has got, you know, curly braces. We only use curly braces when we talk about, concept of set, right? This is how we enclose elements of a set. So are we really dealing with the concept of a set over here? The answer is, well, yes, we are. Okay, so that's actually the interesting part. Okay, so what we'll do is we are saying, okay, so we are looking at the limit superior of a infinite sequence, which is x. X is the name of the sequence, as n approaches infinity. So we are looking at what if n is getting larger and larger? This is the asymptotic behavior of the sequence. So when we look at this mess here, okay, let's work on this from the inside out. Okay, so we'll basically look at this portion here. Now I have to be very careful of which part I'm highlighting. I'm only highlighting this part here, which starts with a brace. It says xk, and then a vertical bar, x is greater than or equal to k. Okay, this is a set notation. I'm describing what elements is in this particular set. Okay, so this particular set has an infinite number of elements because everything in the infinite sequence where the index is at least n will be a part of this set here. So in other words, if you pick a particular n, okay, then the set that is highlighted here will include x of n, x of n plus 1, x of n plus 2, x of n plus 3, and so on. Okay, is that concept okay? For any particular n, this is going to say, let's look at the elements in the sequence where the index of the element is at least n. Okay, so are we convinced that the highlighted portion is, oh, okay, so we are really just talking about a set? Is that okay? It's a set that is a subset of the infinite sequence. Is that okay? All right. So in that case, we can go ahead and find the supremum within that set. In other words, we're looking for the maximum in that set. Is that okay? Because supremum is basically the same thing as maximum if we are talking about a total order. Are we good so far? Okay. So this is a single value. Okay. If we just look at this one here, the supremum of a set where xk, a set of xk where k is greater than or equal to n, it is really just a single number. It's a single value. Okay. Now that single value is used in the description of another set. So the other set is basically saying, for every n that is greater than or equal to 0, give me the supremum of this particular subset. Are we still doing okay so far with this? Or are we
I think
starting?
I'm following it.
You're following? Okay, good.
I think so.
Yeah. So if you expand this, okay, if you expand it, this notation here, okay, it is just going to expand to the supremum of, starting with 0, the supremum starting with 1, the supremum of starting with 2, the supremum of starting with 3, and so on. And then what do we do with this larger set of values? Let me just make sure that we know which set we are talking about. So what are we doing with this larger set of values? We take the minimum of that. In other words, we are taking the minimum of the maximum start with a different starting point of the sequence. Let me say that one more time, okay? We are taking the minimum of the maximums of the infinite sequence, but starting at different points in the sequence. Is that okay? So this is the maximum of the infinite sequence starting at the very beginning. This is the maximum of the infinite sequence, but skipping the first element, starting with the second element. This is the maximum of the entire infinite sequence, but skipping the first two elements in the sequence, and so on. And then we look at each maximum and ask what is the minimum of all of these maximums. That becomes limit superior. Are we doing okay or not?
Trying to find the smallest number approaching the limit, right? Or rather, we are taking the smallest we're taking the smallest maximum and calling
It's
that the limit.
it's not quite taking the smallest of the maximum. It is taking the smallest of the maximum starting at different points of the sequence. So they're not exactly the same thing. Okay, so let's use an example. So I think an example can be helpful in this case. Okay, so we'll start another example. So this is the index. Once again, the index starts with 0, and then we're just sequentially going up, as natural numbers. Okay, so a bunch of natural numbers like that. And this time we have to define the x of I so that it is not a monotonic function. Because a monotonic function, it doesn't help to illustrate the concept of limit superior. Okay, so we have to find something that oscillates. Okay, and the oscillation does not decrease in terms of amplitude. So sine, cosine, those are all applicable functions because they're all cyclical and they do not settle. Okay, so we'll go ahead and define x of I as I times pi divided by because I have to give it a period. The waveform has to. I don't want it to be just flipping between 0 and 1, 1 and -1. So we'll go ahead and say let's pick an odd number. Okay, there's no reason why we cannot pick an odd number here. Okay, so this becomes the angle, and we're looking at the sine of that particular angle. Okay, so sine of 0 is definitely 0, but you can definitely see that it is kind of cyclical. You can see how it goes from 0 to 4, gets kind of close to 1, and then it gets smaller and smaller, goes negative, and then go back to almost 0 over here, and then go positive again. So it keeps oscillating. Is that okay? Does everybody understand what xi is? It really is just an element in an infinite sequence, and in this case, this infinite sequence keeps going up and down and up and down. It never really settles on a particular value. Are we good so
Right.
far? Okay, good. Okay. So now we want to look at supremum. Okay. So we have to pick a particular n in this case. Okay. So we have to pick a particular n, and I'm just trying to figure out, how to do it, how to express this. Okay, I think I got it. Okay, so this is the supremum, or the quote-unquote maximum of xk, where k is greater than or equal to I, which is column A. Okay, so basically we are just okay. So I have to extend the sequence a little bit longer, in order for uh, this to be obvious. So we extend it to. Oh, you guys cannot see this part anymore. Sorry. Move it up here. So we'll just go ahead and extend it to the end of the screen. Okay, so we are not technically dealing with an infinite sequence, but because the period of how the numbers oscillate is already contained within the range that we can see here, so we can still see the effect of that. Okay, so to express this one, I'm going to use the actual maximum function in a spreadsheet, but I have to be careful of how to specify the range over which we are calculating the maximum. Okay, and if I remember correctly, there's a function called offset. Yep. Okay, so we can look at offset, and the first one is which cell we are referring to. So we are referring to this cell over here. The next one is the number of rows. So the number of rows is going to have to change depending on which one we are talking about. So that's going to be 29 minus the value over here. So it's 29 minus this value. Okay, that gives us the number of rows, and then I think we need a +1 here. So that gives me the number of rows. Number of column is going to be a 1. The number of columns that are moved to the left or the right. Oh, okay, I take it back. So it's B2 with 0 offset, and then the height is where I need to do that calculation. 29 as a constant minus A2 plus 1, and then the number of the width is just going to be 1. So this offset defines over which portion of the spreadsheet am I trying to figure out the maximum. And then we need another close paren, and that should do it. Okay, so this number is the maximum of this entire range of values. Okay, is it obvious that 0.974 is the maximum over this entire range? We got it over here, right? And we don't see anything larger than that. It is repeating over here because we're looking at sign. So that's kind of obvious, right? Are we doing okay so far with this single value? It is a maximum over everything starting with this value and everything up. Are we good so far?
Sounds good.
Sounds good? Okay. So if I extend this down a little bit, does it make sense that they're all the same? Because if I just look at this particular value, it is basically saying what is the maximum from here on? So are you guys convinced that from here, which is B4 and on, the largest value is kind of the same thing, 0.9749 blah blah blah, because that thing repeats a few times within that range already. Does that make sense?
Yes.
Okay. So now if I keep extending this, okay, and once we get past the last time we got that value, you can say, hey, what's happening here? Why is this only 0.781 and not 0.974 anymore? Because from this point and on, the largest value, well, because this is an infinite sequence, right? And I don't have the infinite portion of this. So from here on, it is not going to be 0.9749 anymore. So this is only because we are not really looking at an infinite sequence, okay? If we were looking at an infinite sequence, then every single one would be of this value, okay? And then we take a look at the actual definition of lim sup. So limit superior is basically taking a look at all of these things and ask which one is the smallest. So this is the minimum of all the supremums, starting with different points, and is asking what is the smallest of that. Is that okay? Does everybody understand this one?
I believe I do now. Yes.
Okay, so we can also apply this to the example in sheet 1. So we can go back to sheet 1, and instead of looking at whether something is less than epsilon or not, oh, okay, I forgot to do a Control C first. So we'll do a Control C, and I go back here, do Control V to paste. Yes, we are pasting over. Okay. So within this one, okay, is that okay? Does everybody see how, in this case, the supremum starting with index 0, and it's just the value at that point, do you see how these are the same? How xi is the same thing as the supremum starting at xi, and that's because the function itself is monotonic. It is always decreasing. So everything at this point and after is less than or equal to this thing over here, and as a result, the supremum from this point on is really just xi. Is that okay? So the
Absolutely.
okay, very good. So limit superior for this particular infinite sequence is going to be 0, because remember, I did not quite work on the entire sequence because this is an infinite sequence. It would never end. But if you look at the trend, okay, as column B goes smaller and smaller, column C is following exactly the same way, which means if I take the minimum of column C, it will just basically get closer to and closer and closer to 0 until the spreadsheet blows up because, I run up against the maximum number of rows of the spreadsheet. So is that okay? Does everybody understand limit superior? Yes?
Works for me.
Okay, okay, very, very good. Okay. If you want a kind of more of a visual image of this, it's kind of like looking at, so let's just assume that you're doing a cross-country trip, okay, where the distance is infinite. It keeps going and going and going and going. Okay, so at every single point of your trip, you basically ask, from this point and on, what is the highest point that I would travel from this point and on. Okay, so at every single point you ask the question. So now you end up with a lot of numbers, right? And then you take all of these numbers and ask, what is the smallest of these numbers? Okay, that is what is limit superior. You first look at the maximum starting at different points of the sequence, and then you find the minimum of all of those points. That is your limit superior. Is that okay? Or not? Okay. So, assuming we're good with limit superior, limit inferior is exactly the opposite. Okay, you basically find all the minimums at different starting points of the sequence. Okay, so you start from the beginning, the very beginning of the sequence, and you ask, okay, give me the minimum starting from this point. Okay, here's the number. Give me the minimum starting at the second element in the sequence. Okay, here's another minimum, and then you have the third minimum, the fourth minimum, and so on. So you take all of these minimums, then there's an infinite number of these, and then you ask, what is the maximum of these minimums? That becomes your limit inferior. Is that okay? Are we working okay with the concept of limit superior versus limit inferior? Now, with limit superior, okay, and you're dealing with an infinite sequence that keeps oscillating, it is not a problem. Okay, it is well defined. With limit inferior, you can also find the limit inferior of an oscillating function. It is not a problem. Okay, so this is what the reason why we look at limit inferior and limit superior is basically saying, what if the infinite sequence is oscillating and it never settles on a particular value? These will give us the tool so that we can still have a well-defined value for that particular sequence. We can still describe the asymptotic behavior of that infinite sequence. So are we doing okay so far in terms of understanding why we have to introduce the concepts of limit superior and limit inferior? Okay. All right. So let's see. Let me check the time. Okay, we still got about 8 minutes, so I think we can finish the entire module. We may not have time to have a kind of like I would say it's a interesting example of why time complexity is important, but we'll see. So upper bound, it can now be defined. Okay, so upper bound is defined like this. If you have a function f, which is the exact amount of time that an algorithm needs using a particular implementation to solve a problem of size n, and you have a simpler g of n, which is serving as an estimate of the time complexity of a particular algorithm, the way you relate f and g is like this. F of n, or f itself, is an element of big O of g if and only if the limit superior of the absolute value of f of n divided by g of n is less than infinity. Okay? So you look at this and go like, that seems really kind of awkward. So let's interpret this, kind of from left to right. Okay, the first thing is, oh, f of n is considered an element of big O of g of n. What is that? What does that mean? Well, in the notes here, this is also something that I just added today. It means big O of g of n is a set. Okay, it is a set of functions. It is probably a set of an infinite number of functions, where g of n is a upper bound of. Okay, so this is a set. Okay, big O of g of n is itself a set. Every element of that set is a function, and every function in that set, a g. Okay, let me rephrase it. G of n is an upper bound of every single one of the functions as an element of big O of g of n. Whew, okay, so is that okay? Basically, the big O notation is saying I am an upper bound of all of you, you being elements in the set, and I being g of n in this case. Is that okay? All right. You're still confused. Okay, so which part is the confusing part? That big O is a set, or what is in that set? What is in the set? Okay, so what is in the set? Each element of this set is a function, and if something is an element of the big O set, then g of n in this case is an upper bound of that element. Okay, let me see if I can rephrase this using mousepad over here. Okay, there we go. Okay, so big O of g of n is a set of functions. Okay, so that's the first concept. We are talking about a set of functions, and we already talked about functions before. So each function itself can also be seen as a set of two tuples, but we are not concerned about that at this point. We'll just say that every element of big O of g of n is a function. So now we'll say, what do we know about an element of that? So if f of n is in the set which is big O of g of n, this means, okay, if and only if g of n is an upper bound of f of n. Is that okay? So that really is the definition of the big O notation. Now, the big O notation is abused and wrongly used in many contexts, but big O really is just an upper bound. That's all it is saying. So is that answering Krishna's question, or is it addressing Krishna's question? Yep. Okay. Excellent. All right. So now the question is, okay, what do you mean by g of n is an upper bound of f of n? What does that mean? So that means this is true. Okay. So when you look at this portion here, okay, this is a comparison, and a comparison can only tell you whether it is true or false. So when we look at the lim sup, okay, the limit superior of f of n divided by g of n, if that is a value that is not infinity itself, in other words, if this is not approaching infinity and instead it is a constant of some kind, then we say that g of n is a upper bound of f of n. Okay, so that seems pretty simple, right? I mean, if this thing, okay, if the limit superior turns out to be 5, okay, 5 is definitely less than infinity, that means g of n is an upper bound of f of n. But what if it is a 0? Okay, well, what do you think happens? Okay, what if limit superior as n approaches infinity f of n divided by g of n is in fact 0? It would just get smaller and smaller and smaller. Well, g of n is still an upper bound of f of n. Okay, it doesn't change the fact that 0 is less than infinity. Are we doing okay so far with this concept? Okay. All right. So the English translation, okay, is that g of n is an upper bound of f of n. It also this can also mean for every n out there, there exists a k such that if I multiply k to g of n, that product will be greater than or equal to f of n. Okay, you just need a constant to multiply to g of n, and the product between the constant and g of n is always going to be greater than or equal to f of n. And that makes g of n an upper bound of f of n. So, are we good so far with this? Okay.
I think so.
Okay. So the next item is called what is negligible. So I'm going to skip negligible for now. Okay, so I'm going to skip negligible. Negligible simply means the ratio goes to 0 exactly. So the limit superior, this is not limit superior because it's going to a single value. So the limit of f of n divided by g of n is 0. So I'm going to not talk about negligible because it is not really used a lot when we describe algorithms. But lower bound is important. Okay, lower bound is looking at the same ratio, and as long as this ratio is greater than 0, as long as the ratio of f of n divided by g of n is the limit inferior of this is greater than 0, we call g of n a lower bound of f of n. Is that okay? So what can be greater than 0? Okay, it just has to be non-zero, right? It cannot be negative because time cannot go negative. So as long as f of n divided by g of n and the limit inferior of that is not 0, it would meet this requirement. What if this ratio is just going to approach infinity? Well, it is infinity or something that approaches infinity is still greater than 0. So it will still meet the requirement of being a lower bound. Is that okay? What if it is a fraction? What if it is 0.2, 0.4? It is still greater than 0. So all of those values would meet the requirement of being a lower bound. So I'm going to skip the definition of dominant and then skip all the way to tight bound. So tight bound is what we really, really want. Okay, it is in the form of big theta. So if g of n is both an upper bound and a lower bound of f of n, then g of n is now known as the tight bound of f of n. So this is typically what people really want to get to, is a tight bound. Because what a tight bound can say is we can model the time complexity really well. If I know how much time it takes to solve a problem size of 200, I will know with pretty good accuracy how much time it's going to take to solve the problem. Let's say the problem size is 1000. I know exactly how those two numbers relate with a tight bound. Now, but why not just settle for an upper bound? Because an upper bound can be way over. Okay, so if you look at any type of algorithm that has a time complexity of, let's say, log of n. Okay, so binary search has a time complexity of log of n. Well, guess what? N itself is a upper bound of log of n. So is n squared, so is n cubed, so is n factorial. So if you say binary search is an algorithm that has an upper bound of time complexity of n factorial, that is not very helpful because n factorial grows really, really, really fast. You are just saying that the algorithm is not that bad, okay? But you're not telling me how good it is, okay? Because you're just saying that it is not quite that bad. We know it's not quite that bad, but how good is it? Well, you're not giving me any information if you just say that n factorial is the upper bound of a binary search algorithm. Okay, does everybody see why just because we can find an upper bound is not enough for that upper bound to be useful? Because it can be way, way, way over what it really is. So the same thing applies to lower bound. So if you look at the traveling salesman problem, okay, which is known to be a notorious problem because it has a time complexity of n factorial, and you can now say, oh, I know a lower bound of this particular time complexity of this algorithm is log of n. Oh, great. Yes, it is definitely true. Okay, because very few algorithms has such a really great time complexity of log of n. You can even say that we know that the constant time, which is known as big O of 1, excuse me, f, the function is just a constant. You can even claim that the constant time is a lower bound of the time complexity of the traveling salesman problem. Yes, that is that's great, but how is that going to help me? Because because these underestimates are so below what it really is it's not helping me to anticipate how much time is this algorithm going to take to finish the calculation. You're just telling me that, oh, it's going to be more than this much. How much more? I don't know. It's, I guess, a little more, way more. I don't know. We just know it's more. So that's why just knowing a function that is the upper bound, knowing yet another function that is the lower bound, is good. It's good to have, but it may not be useful. So if you get closer and closer, so that the upper bound gets closer and closer to the actual function, and the lower bound gets closer and closer to the actual function until they are the same thing, then we have a tight bound. Is that okay? Does everybody understand that concept? Because I think this is a good place to stop. So if I want to summarize, okay, this entire lecture, okay, the first thing is the big O notation is often misused in literature, and that includes certain Wikipedia pages. The big O notation, all it is saying is it is an upper bound. Okay, the big omega notation is a lower bound, and then the big theta notation is the tight bound. So a lot of times when people say, oh, the big O of this algorithm is blah blah blah, what they really want to say is the big theta of this algorithm is blah blah blah, because the tight bound, if it is known, is the most useful bound for the time complexity of an algorithm. So if you have to take away just one thing, okay, what I just said is the most important part of the discussion. Now, does that mean limit superior, limit inferior, those things are not useful? No, they're still useful because they are tools, by which we can express what do you mean by an upper bound, what do you mean by a lower bound, and what do you mean by a tight bound. So when we express those concepts, we still need to make use of the mathematical definitions of limit superior and limit inferior, which then relies on the definition of supremum and infimum. But supremum and infimum, as far as real numbers are concerned, are really kind of the same thing as maximum and minimum. Okay, so they're just kind of fancy terms, when we have, some number system, some value system that is not totally ordered. But since numbers, real numbers, are totally ordered, I think we can just substitute with maximum and minimum. So that's kind of the quick summary of today's lecture. Do we have any questions? Can I answer any questions related to today's lecture right away? Because this is a good time. We just got exposed to these concepts, so a discussion right now is going to be helpful if there are any questions. All right, I'm not.
I guess
Yeah, go ahead.
I guess it'd be like the big O would be the worst case scenario, the little O is the best case scenario, and the tight bound is closer to the actual root
So the
of an algorithm. Then
um hmm. I'm just thinking, so
Rather,
I'm
upper bound. Upper bound, worst case, lower bound, best case, type bound, closest to the algorithm's outcome.
I'm not 100% sure that is what the upper bound and lower bounds are about. Um, because if you, okay, think about binary search, okay? So the best case of binary search is constant time because the element right in the middle of the array is the value that you want to find. So you can always construct a best case scenario where the time complexity is useless, okay? It's like, oh, we are there already. Okay, we're done. Okay. Um, so when you consider the time complexity of, let's say, binary search, you kind of have to think about, okay, in the case of binary search, okay, if we have 511 elements in the array, okay, if we are trying to find something that is not in the array, what is the time complexity to come to the conclusion that the value that you're searching for is not in the array? So you kind of have to formulate the time complexity itself to cater for the worst case first. Is that making any sense?
Okay.
And then from that, you basically try to come up with what is considered a lower bound when we already have a qualifier for the problem like that. Okay, so the qualifying description is searching for a value that is not in the array. Okay, so once we put that in as a requirement, then we can look at the time complexity. Because otherwise, it doesn't make a whole lot of sense. And we ask, well, the best case is a constant time. Okay, constant time. And if you look at bubble sorts your best time. If the array is sorted already, bubble sort is linear. Okay, it's not n squared. It is just n because all you have to do is to scan through the array once. You don't have to swap a single time. You're done. Okay, you can exit the loop. So that is not helpful at all when we want to find out what is the behavior of the algorithm because it doesn't describe the usual case of applying an algorithm. If an array is already sorted, why do you bother to sort it again? Does that make sense?
Right.
Right.
Okay.
So you kind of have to formulate the problem to begin with. So in the case of bubble sort, you can say, okay, so we are looking at an array that is actually sorted in exactly the opposite order. Okay, now let's go ahead and figure out the time complexity. So I think that makes more sense. Is that okay?
Yeah.
Yeah. Yep. So even if you do it like that, you can still establish upper bounds and lower bounds, because you can say, well, we know it's not going to exceed, n to the cube, okay, because it's a triple loop, and then within each loop, the number of iterations of each loop cannot exceed the number of elements. So you can quite easily establish an upper bound of it cannot exceed n to the power of 3. But is it n to the power of 3 or is it actually n to the power of 2? Then you can go in and do some analysis and refine your estimate, refine your g of n until it is both the upper bound and the lower bound. Does that make
All
sense?
right.
Yeah, because with an algorithm like bubble sort, you can quite easily say that, oh, the lower bound, one of the lower bounds is just linear, just n. Why? Because one of the loops in the nested loop structure, the top level loop is going to have to go through n iterations to begin with, so we know it has to be at least n. Okay, we just don't know how much it is worse than just n. But you can always say that n is a lower bound. You can always say n to the power of 4 is the upper bound because the loop nested structure is only nesting 3 levels, and then each level can only go through as many iterations as there are elements in the array. So you know that it cannot exceed n to the power of 4. You just don't know how where in between those two bounds the actual function is. So you just have to kind of go like, okay, we know it's at least n. Is it n squared? Oh, okay, we can see that it is at least n squared. We know it is not quite as bad as n to the power 4. Is it n to the cube? It is not quite as bad as n to the cube. Is it n squared? Yep. So now you have established that it is both n squared is both the upper bound and also the lower bound, which means n squared is the tight bound of bubble sort. Is that okay? I mean, is that kind of describing the importance of upper bound and lower bound, and why each one may not be totally useful on its own, but when you move the upper bound lower and lower, and you move the lower bound upper, higher and higher, when they become the same, then you have the tight bound, which is the really useful function that we want to get to.
Okay, I see now.
Okay, great. Yep. Any other questions? So we got Angel asking. Oh, okay. This is from the Design Hub. I'm already bouncing to another channel. Brenda is asking, do you mind summarizing tight bound again? So a tight bound is both an upper bound and a lower bound. So if g of n is a tight bound, then it would meet the requirements of the big O, which is up here. So if g of n is a tight bound, it would meet this requirement, but it would also meet the requirement of a lower bound, which is this requirement here. It will simultaneously meet both requirements. So okay, so let's take a look at that. Okay, if you meet both of these requirements, okay, let me see if I can have both requirements displayed at the same time. Yes, I can. Okay, that's cool. So if this requirement and this requirement are both met at the same time, that means the limit inferior of the absolute value of f of n divided by g of n as n approaches infinity is a constant. It is just a value. Does that make sense? Because it is not infinity, it doesn't keep going higher and higher and higher, and yet it is not zero, so it is a non-zero constant. So as long as you can establish that this thing here is a non-zero constant, then g of n is a tight bound of f of n. Okay, great. Any other questions? These are all great questions. All right. So if there are no questions, I'm going to stop the live stream now, but I will stay online, for a little bit, but only using the text channel to answer questions. So I'm going to stop.